river of ice is on the move, slowly, inexorably toppling into the sea, sometimes in small lumps, sometimes much bigger ones.
So today we'll talk about fluid properties, and so I'll just give a narration different from this. And so some of the fluid properties are fluid exists as liquid or a gas, liquid or gas. And so you'll see all three of those phases, including solid, in this. So that's the relevance.
So what happened there, we got hooked on a piece of ice, we lost the full between the underwater and ocean.
Can we get out of here?
How high do you reckon that is? 40, 50 meters?
That is an enormous block right at the top.
A bit of bravado there, of course.
That whole front is going to go at some point.
Okay, don't worry, they all have happy endings. We don't want to traumatize you in the morning. So anyway, so let me get rid of that. So yes, so three phases of water: ice, solid, liquid, and gas in vapor in the air. And waves. We'll talk about waves in this class as well.
Dirt slicks started appearing, and I thought maybe that's pumice because they're large floating rocks. Then we started progressing into much thicker pumice.
First we thought there was whale poop, and but then it's
First we thought it was whale poop.
way more of it than any normal sized pod of whales could come up with.
Yeah, fine.
When it got to be quite thick, there was no water visible. It was just a field to the horizon on all sides.
So fine. So pumice from volcanic eruptions, lava has gas bubbles in it, vesicles, which make the pumice less dense in bulk than water, and so from Archimedes' principle, it floats. Actually, I should check whether the other one is off. I think sometimes they run in the background, and I don't want that. So this, few years ago.
Torrent of toxic sludge engulfed everything, everyone in its path. Nearly 300 people died here, many in the mine's staff canteen. They just sat down to lunch.
Whoops. So the Berlino disaster in Brazil, it was a, well, let's watch it again. It's not because it's not because it's gory, but part of an engineer's responsibility to uphold safe designs that keep people safe. And so clearly that wasn't the case here. This is a tailings dam. You mine ore, you crush it, you recover the ore from it. It's typically a liquid slurry, and you dump that slurry behind a dam, which is indeed made out of the same tailings. And they're kind of marginally stable. They're solid, but they've got lots of water in them. And sometimes if you hit it, so-called static liquefaction, or if you have an earthquake, you can liquefy it, and the solid turns into basically a liquid that can flow. So again, a phase change of some sorts, which is what we'll talk about. Certainly, it was a solid, and now it's flowing essentially as a liquid. And so, your responsibility to uphold the safety of the public as an engineer, as you will be. And I can't figure out whether this is a spoof or not. You tell me. So terminal velocity. Terminal velocity is defined by gravity pulling you down. The vacuum, you go at 9.81 meters a second. But if air is rushing past you and impinging on your chest, you're destroying the velocity of the air. The air is static, but you're moving at v squared over 2g. And that pressure on your chest is what provides drag, which slows you down to a terminal velocity, about 200 miles an hour. And so in this case, there's a bunch of people filming, but this guy doesn't have a parachute on purpose. So I don't know. So you watch this. Heart rate, 148. Yeah, that's about right.
There goes the oxygen mask. Now at 12,000 feet, he'll hear a beep in his helmet. That will tell him he's halfway home.
You're transfixed. It's fantastic.
Momentarily, we'll see his jump team pull their chutes, and that means Luke is all alone for the rest of the way. At 6,000 feet, he'll get another beep in his helmet. There goes the chutes. Luke is on his own. And the crowd on the ground looking up, they have a visual on him right now. He's in!
Spoof or not, I don't know. So, looks kind of real to me. Certainly the Poseidon adventure didn't seem real, but you could tell that was a model, right? But this, yeah, seems feasible, seems doable. I'm not sure I'd be doing that. No, anyway, so there, again, fluid mechanics, falling through air. Terminal velocity is defined by the balance between forces of drag. Don't know why this won't close. And gravity acting downwards. So, fluid mechanics in normal life. Okay. So let's get down to some work. That's to lead us in. That's our eye candy for the morning. Orders of business, I guess. First, you'll notice that I sent out an email. I didn't mean to send out an email yesterday, but just to note that yesterday's class is online, where it should be. And so if you want to see that, you can. It's edited and put up online. Also, the email mentioned that there are a couple of practice tests. I was fine to send out the reminder, but it was an auto reminder from a previous year when we'd done the tests online. So the two practice tests are online. One's for 15 minutes, and the full test is for 30 minutes. You're welcome to try them. They won't be scored. You can take them as many times as you want. It'll shut down, I think, at 30 minutes, and so you can see the kinds of questions they are. You already have that in your package. I think it's the first test from 2022. 4 banks of tests, 3 midterms, 1 final, and each bank has a Monday, Wednesday, Friday, and it's the Monday of the first bank. So you can see what it is to do it. I should ask, who hasn't downloaded the exams? Am I asking that question the right way? And who hasn't downloaded the homework? So fantastic, you've got them all. So, fine. So you should have done that from last time. So 1.1 is on. You should have, you know where the homework and exams are to be downloaded. I will repeat again, last time I'll say it, the main arbiter of how well you perform in this class, I think, is on the test, just because it's 70% of the grade, and so it's a significant portion. TA office hours are now marked on the syllabus. They won't start this week. I think Isabella's not yet cleared for work, but they will start next week. And I think they're certainly on the days before Thursday when the homeworks are due. Yeah, presentation examples, I won't do those again today. We talked about that last time. So that's fine. Any other business that we should take care of? Questions from last time? A few people introduced me to last time. We have Parker. Is Parker here today? Oh, Parker. Is Tristan here today? Oh. Kieran's here. Is Marcus here? Marcus, you said you weren't ever going to come to class again. So, people were asking different questions. One question that did come up was about calculators. I should write something in the syllabus. They can be programmable calculators. They should not be phones, smartphones. I won't require you to wipe them. They shouldn't be wireless, and they shouldn't have text on them. So, in the spirit of the fact that we have closed book and closed notes. So I've never had to think about that much before, but I'll write something into the syllabus to that effect, but that's essentially the deal. Okay? Questions? No? All right, fine. Well, so we mentioned that in this first week we'll talk about fluid properties, the first. So actually a little bit of a repeat of what we did last time and today in the introductory videos. It'd be useful to talk about the relevance of what you're going to learn to give you some motivation for why you want to know what you're going to be forced to know. You should want to know it. So talking about things in natural systems, in engineered systems, and in sport. We talked last time with Missy Franklin about swimming. But in natural systems, well, the whole Earth works because of plate tectonics. It's the only planet that has active plate tectonics through certain circumstances in its composition and location in the solar system. Plate tectonics has a series of plates floating on magma. The magma is a fluid, a liquid, of course, has gases dissolved in it. And those plates float. They have plate boundaries with subducting slabs, and large earthquakes occur at those, as we know. And those earthquakes can cause tsunamis just by the graphic in the top left-hand side. One part of the seabed rises. It takes the sea above it the same amount of height up. That vertical cliff in the sea can't sustain itself, and so it spreads out in both directions. Is quite short, even if maybe this throw in the Great Japan earthquake was 20 meters, 60 feet. The tsunami traveling across the middle of the ocean, maybe 100 kilometers offshore, is only a few centimeters tall. It's just that when it comes on shore, it gets dragged on its base and it falls over itself, and it builds up to something like 30 meters at Fukushima, overtopping the barriers. Weather systems are fluid mechanics caused by the sun's radiation and the spinning earth that set things in motion. The whole of the Earth's subsurface, a solid crust, maybe 70 kilometers thick, and then mantle that goes down many thousands of miles, which is molten rock, heated up by radioactive decay. Convection is part of the driver that drives plate tectonics and is caused by buoyancy. Heated magma is less dense, so it rises. Cooled magma is dense, and so it replaces it, and hence there's a circulation. Indian Ocean tsunami, as mentioned the other day, we didn't really appreciate how devastating tsunamis could be, even though we've seen characteristics of them in the geological record, say off the west coast of Oregon, where there have been and there will be large tsunamis from the Cascadia subduction zone. Probably in yours and my time. We have the Deepwater Horizon event in your lifetime, I think, right? 2010, your young lifetime. Circulation in the Gulf of Mexico for fluids which floated to the surface, oil and gas, lighter than water, floats on the surface as a slick and is moved by currents. Ice sheets on Greenland are a very slow-moving fluid with a high viscosity, but a fluid nonetheless. And magma at plate boundaries, of course, the plate boundary for the US is the San Andreas Fault, and then the offshore Cascadia subduction zone dips underneath Oregon and Washington State. Magma wells up from the melting of this plate, from the tip of the plate as a volcano, and this would be the right geometry. The volcano's here, and once in a while those volcanoes erupt. This is Mount St. Helens, May the 18th, 1980, which killed 60 people only, not so many, not good for them of course, but also was a disaster in Washington State just by the debris, the ash that fell, shut down airline flights over the country. So again, fluids, magma rising, pressurizing underneath the volcano not being strong enough to resist it. When those magmatic fluids with gases in them are unroofed and the pressure drops, all of a sudden the gas can come out, the magma fragments because it has a gas pressure in it, and it comes out as in this case, as a big lateral blast, which was Mount St. Helens. In engineered systems, well, every time you fly somewhere, you know that you rely on Bernoulli's principle to provide lift to the wings. Deep water horizon. They didn't grout the well in well enough, and hydrocarbon fluids came around the outside of the casing and ultimately into the drilling rig, caused an explosion, and ultimately the linkage at the seabed was broken, and it was just spewing from an open hole the hydrocarbons that were just being discharged into the Gulf of Mexico. Every time you take a flight out of University Park and get on the gangplank that you can see the pilot's cabin on your left-hand side, you see a pitot tube sitting right below the pilot's window. It's a hollow tube. It has a pressure sensor on the back and also a pressure sensor inside the hollow tube. It's the way that you measure the velocity, air velocity of the plane, because the air that comes in through the front of the tube has to stop where it hits the back, and it converts its velocity. Plane's going at a velocity, the fluid is static, so the relative velocity of the liquid is the plane's velocity. So it becomes static, it transfers its velocity to pressure. You measure that pressure inside and outside, compare them, you get the airspeed of the plane. We'll talk about a disaster where a flight from, talk about now, Air France flight such and such from Rio to Paris went through a thunderstorm. This froze, no longer operational. The plane went up and down because it's controlled on a wire, but it also uses the sensors in this relatively rudimentary physical process rather than GPS, and ultimately all souls were lost. And so now these are heated to be able to stop ice forming. Internal combustion engine, becoming a thing of the past with EVs, of course, slowly, but of course compression of fluid, an aerosol, I guess, combustion, a reaction, expansion from that reaction and driving flow. The natural gas and hydrocarbon pipe network in the US, which supplies gas from the Gulf of Mexico to New York City. Some of it rests in New York State in big underground salt caverns, which are solution mined so that you can get it quickly when everyone turns on their toasters in the morning in New York City. Marcellus Shale, again, transport of gas along a pipeline, porous media flows in the shale, making it a larger permeability by hydraulically fracturing it, by making larger porosity and larger permeability, and which has allowed shale gas to be produced. Deep underground geothermal energy, the new possibility for the future for sustainable energy. Environmental systems engineers cleaning up underground storage gas tanks that leak. Energy engineers with single-axis wind turbines, and articulated energy devices for wave energy in the ocean, where the articulation turning this joint provides a motion which you can turn hopefully into electricity for renewable energy. And of course the Tacoma Narrows Bridge, which is a study in resonance, from like a guitar string, the bridge being put into motion by the steady flow of maybe a 30-mile-an-hour wind down Puget Sound, which excited it in motion, that finally destroyed it. Which you can, of course, if you see utility cables here, sometimes you see them on long spans. They have weights on them, not the big orange weights that stop planes crashing into them, but just small weights that damp out, change the frequency of this, and make them not oscillate. And fluid mechanics in sport. Top left-hand figure, too early for you. I think this was the 2000 Sydney Olympics. Everyone was wearing full body suits. Ian Thorpe was the phenom from Australia. Phelps was just getting going. I think they had a big battle together in that. I think Phelps came out maybe on top. Certainly did in the long run. But these were used because these suits allowed air bubbles to form on the skin, and those air bubbles would then provide less drag to allow you to go faster through the water. I'm not sure why they stopped using them. Perhaps there was unfair advantage or something, but now the guys just wear shorts. The America's Cup, I can't remember when, it was probably way before you were born, but the America's Cup never been taken away from the US. The US would take on whatever countries off Newport in Rhode Island. They'd always win in their 12-meter boats, which are actually much longer than 12 meters. 12 meters is some kind of sum of the keel and the beam and the height of the mast, etc. But the innovation for the Australians was to put a fin on the keel. And it was hidden with a shroud every time the boat went into the water. And it was a big mystery. And the Australians won and took the Australia's Cup. The next meeting was in Perth on Western Australia. And so it was revealed partway through the races. The American boat tried to add it, but they weren't quite as successful as this design, which the Australians had, and the cup was lost. Sails on ocean-going boats, you can think of them as being something to catch the wind, but really they're a bit like airfoils on the wings on planes, as indeed are the blades on wind turbines. And so we'll talk about lift and drag on wings. Kayaking, so surfing West Virginia, you can stay in place on a wave by having the water rush past you, being facing upstream and being on the front of the wave and traveling down the wave. So gravity, like the skydiver, is pulling you down, but viscosity of the water along the bottom of your boat is pushing you up the wave. And so there's some subtle balance between there where you can just sit on here and not move if you're skillful, more skillful than I. Snowboarding, same idea. The velocity you go down slope is a combination between gravity dragging you down, drag on your body, and also drag on the bottom of the snowboard, which is also melting the snow, changing it from ice into liquid water, which is a good lubricant. Spinning of baseballs, spin it so the drag is differential on the side and makes it turn in a curved path. And we talked last time about why you dimple golf balls. The airflow over the golf ball changes from laminar to turbulent earlier at slower velocities. And so you reach that for a less hard whack. And so the ball, as a result of that, will go further with the same impulse to it. And so that's why golf balls are dimpled rather than smooth. So that's why we should be hopefully interested in some of the things that we're talking about today. Whole bunch of equations. I almost never use those now. But what we'll do today is go through, this is kind of the pace sheet of what we'll talk about today. We'll talk about liquid, fluid is a liquid and a gas. We'll go through some ideas of dimensional homogeneity. All equations should be the same units on the left and the right side. You can tell if an equation's wrong if they're not, but you can't tell whether it's right. So we'll talk about that. And we'll talk about essential fluid properties of mass, its state. From its state comes compressibility, and we probably won't get below those. So we'll stop there. So that's the plan for today. So this is my style of doing these things. This is my crib sheet. So in terms of what we'll talk about. And so let's get going. 1, 2, right? Might take a while for my handwriting to improve. Can you read that? In terms of size and coherence? So, yes? Fine. So we'll talk about the different states of a fluid, solid, liquid, and gas. So these are the states. We can imagine each of these little boxes containing fluid. And so we know that a solid, if I had a board duster, you apply a force, it displaces, but then it doesn't displace anymore as you apply that force. So it's we know what a solid is. This would be ice in the case of water. We know that liquid is something that sits and fills the container to which it sits in, but it will always have a free surface within it if you don't fill that liquid up to the top. And a gas will completely fill the container it's put into, and it will change its characteristics, its pressure and its density, to be able to conform that. Maybe both of those or maybe one of them to be able to fill that. So we can describe these behaviors in terms of their properties, I suppose. So I'll use uniquely, I said we won't use the book in this class, but it might be a useful reference to you, even this edition or prior editions. We will use exactly the same terminology as that book. So we define density. We use the parameter rho, not to be confused, Greek rho, not to be confused with P. It's a mass divided by a volume. And for us, I will always use SI units. I apologize that some of the units in your assignments are in English units, but perhaps you have to use that. Certainly the petroleum industry is full of English units, so that's perhaps not terrible practice for you. But certainly all the things I do in class and your tests will all be in SI units, primarily because I can't use English units. Isn't that ironic? And so the SI units for density are kilograms per meter cubed. We also might do, I thought about this morning, is we also might talk about the SI multiplication of units. So giga, mega, kilo, not sure what the unit is, and it's milli, micro, nano. So this is 10 to the 9. This is a million. This is 1,000. Kilogram is 1,000 grams. 10 to the minus 3. 1,000 millimeters in a meter. 10 to the minus 6. A million microns in a meter. And 10 to the minus 9 for nanometers. So those are useful numbers to remember as well. So a kilogram is 1,000 grams from that. So for these, should I try using different colors? Be adventurous in this. So density of a solid is high. Didn't use it. Density of a liquid is quite high also. Density of a gas is low. And so typical liquid would be water. A typical gas might be air, of the order, roughly. So they're 1,000 times different. Viscosity. We use Greek mu. And don't worry about this for now. The units of mu are in newtons per meter squared times seconds. This is squared. And it conforms to, as we'll find out, Newton's law of viscosity, where shear stress is equal to viscosity times a velocity of the fluid divided by a length. Don't worry about that. Viscosity is a property. You know what viscosity is. Honey has a high viscosity. Air has a low viscosity. And so solids such as ice have a very high viscosity. Liquids have a moderate viscosity, and gases have a low viscosity. And so the viscosity of water, if we're talking about that, is something like 10 to the minus 3 Pascal seconds. Not going to ask you to remember these. A Pascal is a Newton per meter squared. And a gas, air is at room temperature, is something like 10 to the minus 5 Pascal seconds. I'm just showing off that I know something. I can remember these things. You can make yourself important if you can remember critical numbers and use them cleverly. Modulus. Talk about this. We'll use the letter E for Young's modulus. It's defined in terms of a change in pressure that you apply and a change in volume of that solid over a reference volume, V0. Its units are in newtons per meter squared, which are also pascals, since we used it here. And if, again, we want to define this, I was trying to turn this into a different color. Why don't I do that? So solids have high moduli. Maybe rock is something like 10 gigapascals. Oops. Sometimes my stuff goes crazy. Control Z should back it off. 10 GPa, which is 10 to the 10 pascals for rock. Liquid, surprisingly, water is actually quite a high modulus as well. If you have water in a bicycle pump or in one of the super soakers, and you push down on it and you put your finger over the nozzle, it doesn't move very much. Water has a modulus of something like 2 GPa. Rocks might be higher. It might be 10 GPa, it might be 50 GPa, but water is of this order of magnitude. And air has a low modulus. It's actually equal to, as we'll find out in a minute, equal to the pressure that's around us. So we'll talk about absolute pressure today. This absolute pressure in this room is 1 atmosphere. 1 atmosphere is equal to 100, roughly, 101 if you want to do it properly, kilopascals. Absolute. So this is absolute pressure. And so the corollary of modulus is compressibility. And so petroleum engineers will always use compressibility of a gas to solve the flow equations. Compressibility we'll call beta. I think the book does, I'm not sure the book does or not, which is 1 over modulus. And so the units of this will be equal to inverse pascals. So this, this is pressure atmospheric. Perhaps I shouldn't use it. P sub A, atmospheric pressure, and this is pascals. So perhaps make the distinction for that. And so the corresponding values for this would be that compressibility of a rock would be low, the compressibility of water is low, and the compressibility of a gas would be high. So that's my notation. So we'll use that terminology as we go through this. So that's the principal units that we'll use. Let's talk about what do you call it? Dimensionality. Yeah. And so that was what I mentioned to you before, that an equation should have units the same on the left side and the right side. All your calculations should have the correct dimensions to them. And so what's the best way to show that? Well, what happens if you want to measure the area of a square? X1, X2, Y1, Y2. Let's see if this works. I'm going to try it. Oh, look at that. He's an artiste. A piss artiste. What's the area of a square? You know this. Through the limits, which is equal to x2 minus x1 times y2 minus y1. So the reason for showing this is that the dimensions of this are length. The dimensions of this differential are length. And so when you do the integration, you end up with length times length, and you end up with length times length. And of course you know that the area should be in units of meters squared, which is the same as length squared. So both sides of that expression should make sense. It doesn't matter that these are derivatives. When you do the integration, they'll turn out. It doesn't matter that these are in an integral, or if they were in a differential equation, you could treat them in exactly the same way. And you can work out that indeed the left-hand side is equal to the right-hand side in terms of units, in that the units of A are equal to L squared. And so, well, not L squared, are equal to X times Y essentially. And this is L squared. So the units match. So this is my thing, not that they're equal, but the units match. So you don't know you've done the calculation right, but you know that units should. The exception, of course, is for the petroleum discipline, where all the equations don't match across them. Lots of the equations don't, because you have to use units that are barrels per day and viscosities, there's centipoise, and they're very specific to the units. And only if you use those exact units do you get the right answer on the left-hand side. Everything we use, I don't think there's a single equation we'll use where it isn't true that the left and the right-hand side should be dimensionally homogeneous, same dimensions. So that's a simple example. If we try a more complex example, say Bernoulli equation, I'm going to go, it's not, perhaps I'll put my, so for flowing fluid, you probably have seen Bernoulli's equation before in your background. We'll use, I keep on touching the little pen thing here, which it doesn't like. We'll use X. Like the book, we'll use Z as positive upwards. And you can imagine that in this flow tube, you'd have a velocity 1 and you'd have a velocity 2. They could be different. They'd represent points. That point might have a location that would have an elevation relative to a datum, which we'll call Z. Also at this point, it could have a pressure, P2. And so the only expression we'll use in this class is Newton's second law. Mass times change in velocity with time. This is what acceleration is. And we can look at the units of this. The units are going to be mass. A velocity is a length over time divided by a time. So this is going to be the units of this, which will be mass, length, time minus 2. And the utility of this is that in our expression, you should have probably have seen this, but you don't have to have seen this today for this class, is that we can write this in terms of the elevation plus the pressure over density times acceleration due to gravity plus v squared over 2g. And that is Bernoulli's equation, which is constant. So these individual terms, this represents velocity head, pressure head, and elevation head. Elevation head is potential energy. This is pressure energy, and this is kinetic energy. You can think of them in those terms. This conforms directly to the inertia term. You have a block, you want to accelerate it, you have to apply a force to make it move. If it's moving and it stops, you have to apply a force to stop it. Leaf blower on my chest, the air is traveling at some velocity, it stops, it's traveling with a velocity. If you destroy that velocity, it'll exert a pressure on my chest that has to exert, because we can write Bernoulli at two different locations, where it comes out of the leaf blower, where it hits my chest. So these have to be, from what we've said before, dimensionally homogeneous. This is a length, so the units of this have to be in units of length, in meters, so we know that. We could manipulate these to be able to find out what their units are. I won't do that today, but I will play a couple of games with this just to show that we can manipulate this in a simple way. And I will take these two first. Since they're both units of length, I could take P over rho g, and I could divide that by v squared over 2g. And if I do that, I get the units. I won't worry about the 2. I'd get the units of pressure over rho v squared, which is equal to pressure force over inertia. And so this is called the Euler number, after the famous Swiss mathematician. It's always the units of pressure and inertia, and you could use this to say how this impinging jet of air hits my chest, changes from velocity big away from me to velocity 0 here. And if you know the velocity and the density of the fluid, you can calculate the pressure it exerts on my chest. A unit, a number that we'll use a lot. If we use these two, I guess I'll go with another. It does a straight line at some stage. So these two, I'll get faster as time goes on. We get, what do I want to do? I want to do, okay, this one over this one. So v squared over 2g. And I want to divide by 1 over z, or multiply by 1 over z, divide by z. We end up with v squared over gz. And I take the square root of this, and I get v over, so v over square root gz. And if you think of Missy Franklin swimming along and the height of a bow wave, see? This says something about the size of that wave that will develop ahead of you, which is what you don't want if you're a swimmer, because you've got to punch through that. You're piling up this water in front of you, and of course you're lifting it from the surface of the fluid ahead of you, and maybe lifting it up 5 centimeters. And so you want this to be as small as possible. So this is called the Froude number, F-R-O-U-D-E number. And it's the ratio of inertial forces to gravity forces. Gravity. Do I want to do it? No, I won't do it today. So we're not finished yet. I need another piece of paper. See if I can do that. Can I add one? Do I know how to save? Add page. Genius boy. That's me. All right. What else do we want to do today? We've talked about these components. Let's talk about phase changes. We've talked about solids, liquids, and gases. Before we get there, maybe what we'll talk about is absolute scales of pressure and density. So pressure would be something like this. This would be our datum. Let's go blue and talk about absolute and gauge. G, gauge pressure. So this is absolute pressure is 0. This is where we're sitting at atmospheric. This would be 101 kPa. It would also be an atmosphere. It would also be a bar, 1 bar, for barometric pressure. So in atmosphere, absolute pressures, these would be where we are now, roughly 101. In gauge pressure, this would be 0 gauge, and this would be minus 101 kPa. That's important because when we look at the ideal gas law, absolute pressure is equal to density times a gas coefficient times the temperature. P sub A is absolute pressure. T sub A is absolute temperature. And we need those to be able to link those. This is the gas constant. I'm not clever enough to tell you what that number is, but we can perhaps do that next time. Gas constant for a particular gas, for gas I. Or we could also write it as atmospheric pressure is equal to density, which is equal to the universal gas constant divided by the molecular mass of that gas, again times T sub A. And we could also write that, if we wanted, as absolute pressure is equal to some mass over volume, which the density is, of course, which is equal to R over mTA. So the corollary to what's on the left-hand side would be temperatures. And temperatures are in the same scales. And they come in the 2 same varieties as absolute and, I don't know, what do we call it? Don't call them gauge. Call it Celsius, I guess. After the Swede, an absolute would be Kelvin, degrees Kelvin. After Lord Kelvin of Glasgow, named for a stream that goes through near Glasgow University. And so in absolute temperature, degrees Kelvin, this would be absolute 0. This is where we sit today, a bit hotter than this today. This would be 273. No, sorry, okay. This would be, not today, this would be 273 Kelvin, and this would be 0 degrees Celsius. This is probably closer to where we're sitting today, at 20 degrees centigrade, and 293. The equivalent of Kelvin from a 0 is Rankine and Fahrenheit. So Celsius and Kelvin are the same as Fahrenheit and Rankine. Don't talk about those. They're excluded to us. And of course, this would be minus 273 degrees C. So we need to remember that. Well, got 5 minutes to go. See if I can be super clever now. I've stunned myself already with my stupidity there, but yeah, come on. Let's see if I can do this. See if I'm skillful. Oh, yes. My fingers are sweaty or sticky. I have a favorite one, but I don't see it really here. Which one do I want to use? One without too much annotation. Oh, that's good. See if I can do a screen capture. Oh, what? Almost. You're putting bets on me getting this right? Who's... Whoa! Look at that! Is this boy a genius or not? So, I can't use this. My fingers are sticky because it's so damp today. So, we're interested in phase behavior. Perhaps we won't get through much of this today, but we know that for water, these pressures that we've talked about are in absolute pressures and temperatures. This is not absolute. This is in Celsius. Pressure, by the looks of this, is in absolute. And so where we find ourselves here is, this is where we are in this room. I guess I need to attach that. So this is where we are in this room. I would guess that we are probably here, 20 degrees centigrade, something of that order. So that we know that if we change the temperature to 0 degrees centigrade, it will turn to solid ice, the water that we have. We know that if we sit in this room with your beaker full, it will stay as liquid water until you boil it to 100 degrees. And then as you go above 100 degrees, this is the vapor point on this line. This is where it will change from a gas to a vapor. That means that at whatever pressure you're at, if you're sitting on the top of Everest, I don't know if that would be the pressure, then your water would boil at only 40 degrees centigrade. So it matters what the pressure is. And so the classic question is, how does it take longer or shorter to cook something on Everest? No. Longer. It only gets up to 30 degrees and it boils. And it can't get higher than 30 degrees. So you're waiting for, you might never cook. Don't cook pork in water. You'll get trichinosis on Everest. It takes longer. Right? That's the rationale. It can only get up to 30 degrees and then it'll turn into vapor. And you only get from the cooking part, immersed in the liquid, the benefit of the temperature of the liquid water. So good for going out after it, but that's the deal. It's the same as the joke. The guy's out in the woods and they come across a grizzly bear. The guy gets down, one of the two guys gets down and puts his running shoes on. The guy says, well, you can't outrun a bear. He says, I don't need to outrun a bear. I just need to outrun you. Not funny? Not funny. Well, we're getting to the. So anyway, so phase diagrams allow us to move between different components. What we'll learn next time is that we've already said something about it, and I'll write it properly, is that for vapors, pressure absolute is equal to density gas constant times absolute temperature. We can use that to say something about the modulus of gases at temperatures. We can use that. We use a different rule to say something about the modulus of solids and liquids, and we'll deal with that maybe next time. Great. Any questions? I left you a minute.